Okay. Good morning, everyone. I want to welcome you to another statistical machine learning class. Of course, statistical machine learning is like a story that goes on and on and on. What we're going to be doing today is also very, very crucial. And I will advise that you pay attention, listen, or where you get stuck, ask question. Does that make sense, everyone? Okay. Uh, on Monday, I started ad clustering, situation where I actually want to classify objects into different groups that we call clusters in such a way that a particular object cannot belong to more than one group. Now we got algorithm for hard clustering. I believe I walked you through the K-means on Monday. The next in the line of the algorithm for hard clustering is what we call the K-Medoid, an hierarchical clustering. So a quick look at the outline. Of course, today our focus is going to be on K-Medoids, an hierarchical clustering. Okay, this fall under hard clustering. We're going to look into how the algorithm works, including processes, the application, and how can we actually evaluate the optimality of the number of clusters. Then we're also going to look into the drawbacks. Let me tell you this. We have several methods in the world. We have several techniques in the world because of the fact that every technique actually has a drawback. If there is no drawback, of course, maybe in the world, we're only going to have one technique. Okay, then how do we also implement that in now? Also going to walk you through that. Okay, but you know what? Four of us want to remind us that we got our algorithm, for hard clustering. And what I mean by hard clustering is that when I classify objects into group, that object cannot also be found in another group. There is no probabilistic assignment. Okay, here. Okay, and of course, I've walked you through the K-means. Okay, let's go to the K-Medoid. And I'm quickly going to, you know, uh, summarize this. What is the difference between K-means and K-Medoid? Or, or let me just say, why do we need our K-Medoid? Why not just be satisfied with the K-means? Let me tell you this, the K-means is highly sensitive to noise. When your data is noisy, okay, the K-mean, because K-means algorithm relies on the mean. And from statistical perspective, mean is sensitive to outlier. Mean is sensitive to noise in your data. Now, when we're using K-means, uh, ahead of time, we normally have a predetermined number of clusters, and when I randomly assign observation into different clusters, then the next is to find the average in a particular group. The average in a particular group is called centroid, but situation where your data is noisy, like I said, finding average, okay, average cannot be trusted. Now, instead of forced to find average, can we just look for a particular data point, okay, within the observation to serve as a centroid? But instead of us to call it centroid, we're going to call it medoid. Okay, the idea of the centroid, has to do with the average. But medoid, we're not talking about the average now. we actually want to use a particular data point to serve as the center. Okay, we want to use a particular data point to serve as the center, and that is exactly the difference between the two. Okay, and let me tell you this. Because of that, we before we can choose a particular data point to serve as a medoid, we have to look at the closeness. Okay, we have to determine the dissimilarity between that particular data point, okay, and the object we are classifying. And that's why you're seeing here, this is absolute difference between the object and the particular data point that we're going to choose that will serve as a medoid. Now, the name of this distance is called Manhattan distance. But I remember in the K-means we use Euclidean distance. So in the medoid, we're using Manhattan distance. And what we try to do here is to minimize the difference. We want to minimize, okay, the difference, which means object that will be classified into a particular cluster with a particular medoid, that very object, the distance should not be, it should be minimized. The distance of that object to that medoid should be minimized. Okay, and because of that, okay, we actually going to run into optimization problem here where we are seeking to minimize what we call the total distance. Okay, this is the objective function now for the K-medoid. We are actually putting into consideration the distance, okay, the distance between the object and a particular data point that will serve as the medoid. And the data point that will serve as the medoid is not a centroid. It is not an average. And I told you the reason why we're not using the average is because the average is actually sensitive to noise. We could have situation. I remember in the, early in the semester, where I said the data could be noisy, the data could be biased, the data could be structured, the data could be unstructured. So what if in a situation where the data set as a noise, then the K-means algorithm is not going to do a great job. Okay, now this is the process. Okay, if I want to actually use a K-medoid, this has a similar operation with the K-means, of course. They both involve. I have to predetermine the number of clusters, then I have to assign observations into group. And after assigning observation into group, the difference is going to be in the K-means. I'm actually going to get the average of a particular group, which make it a K-means. But in the case of the K-medoid, I'm not finding an average, but I'm actually going to use a particular data point to serve as a medoid. And from there, I'm actually going to have an objective function, okay, that will minimize, okay, because we're going to have the sum of dissimilarity for all instances. Can I add because you got a lot of objects, okay, on each object, if you consider this object, what is the dissimilarity between this object and what serves as a medoid? We're going to do that across objects, and that is going to be called the sum of dissimilarity. And what we want to do to the sum of dissimilarity is to minimize that. Okay, now let me tell you this. You know, because of the fact that this is an iterative algorithm, K-means and K-medoid, they are all classified, they are iterative algorithm. There's going to be a lot of iteration, but let me tell you this, it could take K-medoid algorithm to converge to a true value a longer time than K-means. And if I really want to know the iteration running time, okay, is what you see here. Is the square of the number of clusters and the number of data. If I really want to know, because don't forget, um, we may need our result in time, in time, and we actually want an algorithm, that we converge faster. So if you really want to know, the time analysis, that's exactly what I'm trying to show. Okay, now I need you to pay attention before trying to use. I'll try to do this in R. I need you to see. I want to walk you through this manually, okay, using some set of data, how the K-Medoid is going to work. Are you all ready? You all ready, right? Those of you at the back, are you all ready? You listen to, you getting what I'm saying, right? Now, I want us to take a look at this. We want to have a demonstration now. How the K-Medoid work? Now, you have how many items? 9 from 0 to 8. These very items, we want to classify them into groups using K-Medoid based on certain characteristics. The characteristics is X and Y. Okay. I can only classify, if I want to classify this class into a group, I need to have what is the characteristics for the classification. Do I want to classify you based on maybe your sports, your favorite sports, or do I want to classify you based on the numbers of hours you study and so on like that? So you're always going to have features. Here, I'm assuming we have X and Y. For every observation, okay, you collected, if I'm assuming these are 9 patients that visit my clinic, please pay attention. When you pay attention in my class, you listen to what I'm saying. If you get stuck, you ask question, you're actually going to be totally fine in my class. That's what I'm saying. That's a deal, right? Okay, now I want us to go practical. I have 9 patient visiting my clinic. When patient visit a clinic, they're going to give you a questionnaire to fill. They're collecting your data. Now let's say uh they collected data over 2 variable X and Y. Now you understand this data now, right? Okay. Now to treat my 9 patients that I have, I want to classify them into categories. So that if I classify them into categories, I'm actually going to offer the same treatment to patients in my category, in a particular category, or if they have the same ailment. Now, that's exactly what I want to do. Now, I want to demonstrate K-Medoid. With the K-Medoid, I'm actually going to choose randomly. Let's say, for instance, I'm thinking to classify them into 2 groups. Don't forget, with the K-Medoid, with the K means you need to be able to determine ahead of the time the number of groups you want. Even though at the end of the day, we're still going to figure out, we can see optimally determine, what the numbers of group is going to be. But when you are starting at initial stage, okay, maybe with your domain knowledge, you need to be able to okay, let me start with these numbers of groups. Now, right now, I want to start with 2 groups. If I want to start with 2 groups, then it means with the K-Medoid, I'm actually going to choose 2 data points. Now, if I choose 6 and 7, please pay attention. 6 and 7 means I'm choosing item number 3, maybe patient number 3. And patient number 3 has 6 and 7. Can you see that? Then maybe I choose patient number 5 with 7 and 9. That will form group 2. What I want to do right now, I'm now going to be using the Manhattan distance to compute the dissimilarity. Take a look at this. What am I doing here? Okay, the observation that I did not choose, 5 and 6, I'm actually going to look at the equilibrium distance from the 6 and 7. Does that make sense? I'm going to do 5 minus 6, then 6 minus 7. Okay, the absolute value means I don't want a negative. At the end of the day, see, I have a 2 here. Now, with this, I've been able to find all of this. I will do the same thing for 7 and 9. I find all of this. But let me tell you this. If I want to allocate, pay attention to what I'm doing. Okay, if I want to allocate now, I'm actually going to compare. Okay, I'm actually going to compare. Take a look at this. I'm going to compare that 2 and 5. Then the minimum will be in group 1. That's why I said C1. The minimum of that will be in group 1. Okay, take a look at this. Comparing this with that. Okay, that is group 1. With that is group 1. Okay, but take a look at this. Oh, the minimum. Okay, if you take a look at this fall under group 2, can you see that one? Okay, the minimum will be group 1, the maximum will be group 2. Take a look at that. Now, see what I've done. Oh my God, I've been able to partition now my patient into 2 groups. Is there anyone who have a trouble time understanding what I'm doing here? Is there anyone? Now, you know what I've done now? I only choose 2 arbitrarily. But you know what? Because the algorithm is not only going to consider these 2, it's going to consider the possible one. What I'm going to be doing now is to be updating. Now, take a look at this. I'm going to do something now. I have already classified. I've done my classification now. And the only way to tell if, the only way to tell about the quality of this classification is to determine the total cost. Okay, so what I'm going to do now, I actually want to determine the total cost. And I want to see if because right now, what is the total cost of assigning to these 2 groups? Okay, now if I want to do the total cost, I needed to pay attention. Okay, take a look at this. That guy fall in group 1. That guy fall in group 2. The one in red, okay, is the medoid. The one in red is the medoid. But you know what I want to do right now? I actually want to figure out, I want to find the total, the total cost of my classification. And if I want to do the total cost of my classification, so what I'm actually going to do, if you take a look at this, I want to look into the cost of classifying objects into that particular group. Okay, where is the 2 coming from? Okay, the 2 is actually coming from that table. Okay, if you take a look at this, do you see? Do you see? So what I compute here, they are the cost of classification. So I'm going to add them up. Okay, I'm actually going to add them up. Okay, now that very cost now is 18. Now, if I'm going to base my decision on the meteor, the 2 meteor that I choose, the total cost of classification is this. But you know what? I now want to update. In updating now, I want to see whether if I choose, okay, a different data for the medoid, I want to see whether the cost is actually going to go down. If the cost go down, that's a good deal. Now, take a look at what I want to do right now. Pay attention. I'm going here. Okay. Now, I now want to switch. Initially, please pay attention. Initially, this is what we have. This is what we have. Okay. 6 and 7 is a medoid for the first group, or 7 and 9 is a medoid for the second group. If I want to switch, I'm not going to switch 2 of them at the same time. What I'm going to do, I'm going to start with the C1. Instead of me to choose 6 and 7, I want to choose something else. I want to switch. Okay. Now, when I switch, okay. Now, please pay attention. Okay. Now, if you take a look at this, instead of me to choose 6 and 7, I come here to choose 5 and 6. I want 5 and 6 to replace 6 and 7, but I'm still retaining the group 2. I'm still retaining the whole group 2, but I'm switching a new medoid for group 1. Now, I'm going to repeat the same, but because I'm switching for group 1, I'm not going to call it C1 again. I'm going to call it whole. Now, if you take a look at here now, when I repeat the O process, wherever you see that O, that's a group one, that's a new group one. So what I'm going to do, if I want to justify, if my new medoid is going to perform better than the old medoid, then I'm going to find the total cost of, classification again. Take a look at that. And this time around, the total cost of classification give us 17. But initially, what was it? Initially, it was 18. That was a gain. Does that make sense? That was a gain. Okay. So if you take a look at what I have now, and that was why I said, okay, that was why I said the cost of swapping midoi C1 with 0, okay, is actually -1. Okay. And I said swapping C1 with 0 give us a better clustering. When you have a reduction in the cost, that give you a better clustering. Now, let me tell you what I'm showing you right now is what the algorithm is going to be doing behind the scene. Algorithm is going to continue like that and start doing that until it eventually converge. So what I just show you now just to unravel what is going on behind the scene. Does that make sense? And this is going to keep going. Now I want to move right now. Okay, I actually want to move. Okay, let's look at the advantages. Very easy to understand. You can see very easy to understand and implement. I'm talking about K-Medoid. And, it's fast and it converge in a finite number of steps. I told you the other time, the product of the square of the number of cluster, and, n minus k is actually the convergence time. Okay. It's less sensitive to outliers than the other algorithm for hard clustering. Okay. So, but you know what? The reason why we are going to have another set of hard clustering is because of the fact that k-means and k-medoid, they also come with their own drawback. Okay, what is a drawback? Take a look at that. Okay, it's not suitable for clustering not spherical. In this course, we're going to talk about spherical at their situation, or where the cluster is going to have a regular shape. So this is not good for that. Then if you have different runs, okay, if you have different runs, okay, with this, you're going to have different results. With different runs, different results, okay? And of course, it work efficiently for small data. But what about, large data set? That's going to be an issue, okay? That is a drawback. Now, I need you to pay attention now. How do we do this in R? How do we do the K-Medoid in R? I want us to use the same data set that we used on Monday, USRS. Okay, we have data collected over violent crime variables in the United States in 1973. Okay, over 50 states. And of course, if you want to have access to the data, the same packages that you loaded for the K-means, of course, you have to load all of that. And of course, with this, you're going to have access to your data. And of course, if there are situation where you have a missing data, of course, both K-means algorithm and the K-medoid require you having a complete data set. And that's why now, you need to have a way to deal with the missing data. And after that, we're also going to scale variable because we do not want a situation or where a particular variable will dominate the other. And that's why we're going to scale. Scaling is standardization. Okay. Now, if I want to see the first 6 in my data set after scaling, is this guy. This is the first 6. Don't forget, we have over 50 states. We are only showing the first 4 from Alabama to Colorado, just the first 6 in the data set. We have a variable murder, assault, rape. The 3 violent crime variables are murder, assault, and rape. But you know what? we are trying to include the urban population because we also want to see the the connection, the role, the population of the percentage of population living in the area also play, and that's why we're considering that. Now, looking at the data, okay, you can actually draw a neighbor. Maybe you want to have a sense of what the number of clusters that is going to work. Let me tell you this. Or choosing the number of clusters ahead of time. It's either you are using your domain knowledge, or you can decide to use a neighbor, you can decide to use a gap statistic, and you can decide to use a slope. Okay, so you remember this. Okay, but you know what? Take a look at this. Let's say for instance I start with K equal to 4. Okay, and I set a seed equal to 1 for reproducibility. Okay, the K-med. Okay, take a look at the code now. Okay, K-med, let's say equal to PAM, PAM. That's it. That very PAM is for K-medoid. Okay, then the data is DF here, and I'm actually suggesting 4 clusters. Now, if you take a look at what I'm trying to show you right now, okay, you're actually having this guy. If you take a look at what I'm having now, this is just giving you, uh, you know, in cluster 1, Alabama is one of the members of the state. It's not only Alabama in cluster 1. There's so many others in cluster 1. In cluster 2, Michigan is part of that. Okay. And oh, let me see. Yeah, the ID is just the number, that we give to. Then in cluster 3, we have Oklahoma and others. In cluster 4, we have New Hampshire and others. And of course, what I'm reporting now is actually going to be the average, the average crime rates, for each cluster. Okay. Now, if you want to have a sense to be able to see the clusters, take a look at this. You're going to write our code. Don't forget what I'm putting here is K-med. Okay. This is it. So this is the clusters that we're talking about. You can see states now have already been grouped. Okay. So take a look at that. You see where Florida is, the Maryland, the New Mexico, the Michigan, Nevada, California. Okay. They actually, 1 second, I'm going to do this. Use my pointer. Okay. They actually here. Okay. And of course, the Indiana, Virginia, the like, Washington, here, and so on like that. This is, I think Minnesota is around here, the Minnesota, Wisconsin, and the like. So take a look at that. Okay, now let's say, if we are right at 4, we're actually going to use that in our final model. Of course, this is the first 6. If you want to know uh, the classification of each state, okay, you just do that. You're going to have a lot. But here I'm only showing the first 6. This is telling you Alabama is classified in cluster 1, Alaska in cluster 2, and so on like that. And of course, you are having the corresponding average moderate, initial cluster. Okay. And take a look at this. This is gap statistic that is giving you the optimal number of cluster is 4. Okay. So take a look at that. Okay, now there's something I want to do. We did K-Medoid the other time. If you take a look at these two, one is for K-means, the other one is for K-Medoid. This guy is for the K-Medoid. This guy is for the K-means. Okay, the K-means is suggesting 3 clusters, and this one is suggesting 4. So there can be disagreement. Okay, but let me tell you this. But for you to be able to know whether you should use K-Medoid or you should use K-means algorithm, it depends on so many factors. The number one factor is for you to be able to understand your nature of your data. If your data is noisy, they will prefer K-Medoid. Because using K-means for a noisy data, you're actually going to mislead. Because mean is sensitive to noise. I'm done with the K-Medoid. I want to go to another important clustering that we call hierarchical. Let me tell you this. The drawback of both K-means and K-Medoid is that you need to first specify ahead of time the number of clusters. But what if in the situation where, because the number of clusters that you specified ahead of time is actually going to affect your results. But in hierarchical clustering, we don't specify the number of clusters ahead of time. And that will be determined in the course of the experimentation. Now, I want to welcome you to hierarchical clustering, which is another, important algorithm for hard clustering. For hard clustering. Now, I need you to pay attention now. Look at what I said in number one. The K-mean is an objective-based approach that requires us to predetermine the number of clusters. But here we don't need that. Okay? So which means the answer that it's going to give is random, but for hierarchical is deterministic. Okay? And let me tell you this, and that was what I said here. Okay, this is an alternative approach that does not require you to specify the number of clusters ahead of time. With that, you have eliminated randomness, you have eliminated uncertainty. Because there's uncertainty around when you specify the number of clusters ahead of time. Okay, now we have two types of hierarchical clustering. We have what we call the agglomerative. The agglomerative is when I go from the bottom up. Okay, going from the bottom up means I will first assume if I want to classify everyone in this class using hierarchical clustering, I'm actually going to start by saying each and every one of you, you are in your own cluster. If I have 1,000 students here, I have 1,000 clusters. Then I will now begin to be merging. When I'm merging, I'm actually going from the bottom to the top. And that is what we call the agglomerative hierarchical clustering. We have another one where we actually going to go from the top to down. From the top is actually going to be that, okay, initially I've already clustered, but I'm going to be splitting until I find myself in a situation where a particular, one object, one cluster. But in this course, I'm going to be focusing on the most common, of the hierarchical, which is bottom up, which is agglomerative. But you know what I want to do? Before I start showcasing the algorithm, I think I need to follow for some fold what is behind the scene of the algorithm, and I need you to pay attention. Take a look at this guy. How many objects do I have? 5. With the way they are, if I actually want to use agglomerative, okay, where I want to go from the bottom to the top, then I'm going to start by saying each of these, they are in their own cluster. A is in its own cluster, C is in its own cluster, B is in its own cluster. They are all, since I have 5 objects here, I have 5 clusters. But you know what? I'm now going to be using proximity, okay, to be grouping them into cluster. Okay, can somebody tell me which of them is close that I can put in a cluster? A and C. Thank you so much. Is that what you also want to say, right? Good job. Somebody also raise up his or her hand here. So 2 of you, I can read your mind. 2 of you, send me a message for extra credits. Okay. Now take a look at this. I group the 2. Now A and C now in the same cluster. Then I'm going to consider the next one. You see the other one, they're going to be in the claim cluster. Now, I'm actually going to have a situation now where I'm going to be combining clusters, okay, with a point. Take a look at the next one, the next closest is going to be this guy, right? B is closer to this cluster. Take a look at that. I'm going hierarchical now, okay? Then I'm not going to, what is the next one? The next one is putting this guy there. This guy is close to this guy now. Oh my God. I'm done with the hierarchical clustering. That's what we call hierarchical. Now, at the end of the day, okay, they started with their own cluster, and in the end, okay, we now have them combined. That's hierarchical. That is looking like a tree-like structure. Okay, now I want us to draw this out. What do we see here? Oh my God, look at this. When this is dendrogram, we use dendrogram to depict this guy here. When we started A and C, we started with A and C, right? Can you see the blue? Okay, then we put A and C, the B and A and C together. Can you see the connection? Okay, and after we do the D and E, you see the D and E here in the same cluster. Then finally we merge all of them. Oh my God, the blue dotted line is what matched them together. Is there any question about that? Go ahead. Okay, in clustering, proximity actually matter. I'm gonna go back. Initially, this is what we have, right? Now, if I want to do hierarchical clustering, I consider similarity, objects that are very, very close. That is where I'm going to start. And that was why you all know AC is close, right? I start with that. Then I'm now going to look into the next close one. Okay, the next close one was D and E. And after that, this guy is close to that. Then you see what I did now? Okay. The closeness that we're talking about here is determined by when you're trying to calculate Manhattan distance, which is like this minus this in absolute time. It's like measuring the length. So that's what I mean. Okay, you mean what is it? Can you repeat the question? Oh, okay. I got it now. You are saying that's a good question. You are saying is if I'm trying to tell the closeness of this cluster to B, am I looking at the closeness from A to B or C to B or the average of A and C? Is that what you mean? Okay. Now, I'm not interested in A and C, okay, separately anymore. I'm considering the cluster itself, the distance between this cluster, and that's with now to be able to answer your question. Then I will need to be able to explain to you linkage. But we have different kind of linkage. I'm still coming to that. We have a linkage that will consider the maximum distance, the one with the smaller distance, the one with the average that you mentioned. I'm still coming back to that. That's a good question. You're welcome. Now, after getting this now, from this, your cities, okay? Now, uh, take a look at this. That is where I'm now coming now, the linkages. When I talk about linkages, what do we mean by that? The linkages is merging two clusters together, two different clusters together. Okay, that is exactly what I mean. And that's why the similarity between two clusters is called linkage. So in any hierarchical, when you're working with hierarchical clustering, you need to first determine, like, made up your mind. What kind of linkage do I want? Do I want a maximal distance between two clusters? Do I want the minimal distance between two clusters? Do I want the average? Or do I want a linkage where we can minimize variance within a cluster? Okay? And that's going to lead us here. Can you see that? So we have a complete linkage. We have a single, the complete linkage we focus on the largest. Now, when I have cluster, okay, the complete linkage is going to focus on what is the maximum distance between elements in this cluster. Whether I have a single one, we consider the smallest distance. The average one is now starting to balance. Then we also have the centroid, we have the word. Okay, now as time goes on, you're actually going to see. Take a look at this. For single linkage, I want you to take a look at this. Let's say this is a cluster, this is another cluster. Okay, single linkage is only going to consider the shortest distance between 2 points in the two cluster. Does that make sense? But do you know the problem we normally have with a single linkage? It's shading. Okay, the shading means, okay, it's going to spread out. There's going to be a high degree of variability. For instance, in a New York City where I have a lot of buildings, if I want to put a cell tower on a particular building, okay, and I want a situation where most of the building is actually going to be covered, in that situation, I should consider complete, the maximum distance, so that all buildings are within certain distance. But let me tell you this. The problem with a single linkage is shading problem where there's going to be high variability, but the problem with the complete, where you consider the maximum one, is going to be overcrowded. There's going to be a lot of buildings compacting together. Even though with this we're able to achieve compactness, does that make sense? But overcrowding. Okay, so I'm trying to let you see that. Okay, now this is the dendrogram for this complete linkage. Where I put a dot here is where I cut it. It's very, very important. I want, because you know why? Here I decide that the maximum distance should be 5. It shouldn't be more than 5. In a complete linkage, we consider maximum distance between two objects in two different clusters. In a single linkage, we consider the shortest distance. Okay, in the average, we try to balance things out, but it doesn't really solve the problem in a way. Okay, this is for the average. As you can see, okay, we have the shortcoming. I talk about shading for single linkage, and I talk about crowding for complete linkage. Okay, and with the average, we want to strike a balance, like I said. Now, this is the picture for the single, for the complete, and for the average. Now, I put the shortcomings here. I think I just walk you through this shortcoming. Okay, but I want to come to this practical example. Suppose we want to place a cell towards in a way that ensure that no building is more than 3,000 feet from a cell tower. What linkage should we use to cluster the building? It should be complete, because the complete we consider the maximum distance. You can place a restriction on the maximum distance, but do you know the problem? Overcrowding. There's going to be crowding. Can you see that? Even though you are able to reach all the buildings within the perimeter, but it's going to be crowded. That's all you see right now. The question said, and where should we cut the dendrogram? Okay, to solve this problem. You can do research about that. Because of my time, I'm actually moving. I talk about, let me now tell you this. Your choice of linkage will greatly affect the structure and the quality of your results. So you have to use your domain knowledge to be able to know, what is the choice of linkage that would be appropriate. But let me tell you this, we have a criteria that we can actually use to select linkage. That is the good news. Okay. And what is the time requirement for this to converge? This is what you're saying here. N squared log n. That is the time requirement to convert, because it's an algorithm. I want to walk you through how do we do hierarchical clustering now using the data we've been using. USRS data. I need you to pay attention. Do you know where I'm actually going to start from? I'm going to start by investigating which linkage method should I use. And that is why here I'm specifying the different kind of linkage that I have. And in the end, when you run all of that, let's see results. Oh my God, we actually gonna choose the linkage with the highest value. Which one are we choosing? Word. The word linkage, you know what that means? The word linkage minimizes variance within cluster. The single linkage consider the shortest distance between two objects in different clusters, while the complete consider the maximum distance between them. And the average trying to balance it out. Okay, so we're choosing word here. I'm going to base my analysis on what I choose. You can see now what I want to do. I want to base my analysis on the linkage that I choose. I did not choose this arbitrarily. I actually allow statistical analysis to play out. And after that, I want to generate my, the tree, the dendrogram. Okay. Now doing that, this is what I have. Take a look at that. Now you know, oh my God, you know what I've already done now. These are the states. Give me 1 second. These guys, those are the states in the United States that we want to classify into different groups, putting into consideration the crime variables, the violent crime variables. And let me tell you this, you see the height of this guy. That is about 13.5. That is where we caught the tree. Okay. Now, if you take a look at this, I want you to look at the clusters now. Okay. Uh, you know, you're actually gonna see the one here. It's like if I have a two major, if you take a look at that, those ones are clusters together. You see what we're talking about? So take a look at the Alabama, Georgia, and the like. In Alabama, Louisiana, if you take a look at what I'm saying, the Georgia, the Tennessee, Mississippi, and the South Carolina, they actually cluster together. Okay. And of course, if I want to talk about the dissimilarity now, the dissimilarity between the one here and of course and the one there is very, very high. Does that make sense? Okay, I'm moving. Now, we also need a gap statistic to be able to know the number of groups. Okay. And don't forget, we're actually going to have run that multiple times, 25 times. Okay. And at the end of the day, let's see what we get. Can you see that? This is suggesting 3. Okay. You can see, 3, 4, 3, 4. Okay. At times, okay, we use 4. Because other algorithm, like 4, like 3, let's take a look at that. Then I'm going to do my final analysis on that. So take a look at this. This is for the distance that I computed the other time. This is the final analysis. Don't forget I'm using word because of the fact that it has the IS. And in the end, if I really want to know, it's trying to tell you we got 4 clusters, 7 states in cluster 1, 12 states in cluster 2, 19 states in cluster 3, 12 states in cluster 4, if you take a look at that. Okay. And if I want to say the first 6, okay, Alabama is in cluster 1. And you can see the average murder rate in Alabama. Not only Alabama in cluster 1, there are other states in cluster 1. I'm only showing the forces. How many states do we have in cluster 1? 7. In cluster 2, 12. In cluster 3, 19. In cluster 4, 12. So you can take a look at that. Now, what I'm showing you now is to give you what I call the mean number of murder rates, per 100,000 citizens. I'm talking the mean number here for murder rate for cluster 1 is 14.67. Okay, I wanted to see that. The assault, the urban population, the rate for the cluster 1, the cluster 2, the cluster 3, and 4. Oh my God. What are we going to have next? On Friday, I'm going to walk you through another set of clustering algorithm. This way I'm actually going to stop. Make sure you all stay safe and have a lovely day. But for now, everyone,